Okay, we've talked about the first law of thermodynamics, which is that energy is conserved. We know generally there's two types of ways that I can exchange energy with a system. So if I am looking at the internal energy, I can exchange energy in two ways. Method number one is that I can do some work on the system. Method number two is that I can exchange some heat with the system. Now, today we are going to focus explicitly on the different types of work that we can do. When we compute the work done in some thermodynamic process, we're almost always going to assume that the process is being done quasi-statically. What that means is that the process is almost static. It's almost like you're barely moving. Here's why that's important. Let's say I have some container of gas, and I slam the piston down. So I take the piston, I go boom, make it go down really, really fast. What's going to happen in that case? Well, if I look at what happens in that case, the molecules do not have time to get out of the way of the piston. So as I slam my piston down, they're going to get scrunched down so that if I pull my piston down to this height, all of these molecules right here, all get smushed together. You can see the molecules I've drawn in red are all the ones that got hit by the piston. They're all smushed together so that now the density of the gas is not uniform. I have a much larger density of molecules near the surface of the piston because they're basically just getting smushed up against the height of the piston. They're trying to avoid being crushed by the piston, so they're getting pushed down. Now, why is that a problem? Well, it's a problem because we usually are going to be, using the ideal gas law to compute the work done. The ideal gas law assumes that the gas is in equilibrium. So it assumes my molecules are evenly spread throughout the system. That's not going to be the case if I move my piston down too quickly. So what we want to do is rather than slam the piston down, we want to move it down very, very slowly. Almost so slow that you can't even tell that it's not in equilibrium. We want to move it down quasi-statically, which just means I'm just very slowly moving the piston down. I never move it down. I don't move it down so quickly that the system can't always pretty much be in equilibrium. So we're always pretty much in equilibrium, slowly moving it down. And in that case, what you'll find is that since the gas molecules have time to move out of the way, even the ones that hit the piston will have time to bounce around the container, and the molecules will be uniformly spread throughout the container. They're not going to be all smushed up against the top of or the bottom of the piston. Okay, so this is a very important assumption. It's going to help us make calculations because, again, it allows us to use the ideal gas law. Now, there are many different thermodynamic systems that we can work with. There's magnets, gases, superconductors. Pretty much any macroscopic system is going to obey the laws of thermodynamics. We're going to spend a lot of time with ideal gases because that's kind of the standard prototype system. So to start off with, we're going to compute the work done on a gas. Now we're going to start with just normal everyday gases. They do not have to be ideal gases. But if they are ideal gases, or if they can be approximated as ideal gases, we can use the ideal gas law in this formula. Basically, what's going on is we do work on a gas this way. We push a piston down, and as I push my piston down, that obviously compresses the gas. So I'm doing work on the gas. By pushing on the gas, I'm adding energy to the gas. Now you might ask, what is it about moving the piston down that adds energy to the gas? Well, if it's an ideal gas, the only type of energy is kinetic energy. So let's say say I want to pay attention to this molecule right here. And let's say he happens to be moving upward as the piston is moving down. So he's moving up with some velocity, and he is going to collide with the bottom of the piston. My piston is moving down. If the piston were not moving down, just by conservation of energy and momentum, we'd have a collision against the wall. The gas molecule, which is much smaller than the piston, is going to come up. The piston's not going to move very much. It's basically like throwing a super ball against a wall. The gas molecule comes up, and it's going to bounce back with about the same speed. Now, if the wall is moving toward the gas molecule, the wall's coming down like this, the gas molecule comes up. If the wall's moving down very fast, it's going to knock the gas molecule down. It's going to increase its kinetic energy. So even if it's not moving very fast, the gas molecule's kinetic energy is going to increase. So it's going to bounce back. If this is my velocity going in, it's going to bounce back with a bigger velocity. So I've increased the kinetic energy of the molecule. Therefore I've done work on the gas because I'm increasing its energy. The exact same thing is also true in the reverse direction. The only difference is if you are expanding your gas so that your piston is moving up, the gas molecule comes in, bounces off. Now it's going slower if the piston is moving away from the gas molecule. So we want to be able to compute the work done on this. Now, normally, if you go back to introductory physics, you've seen this equation before, that the work, I'll write it as a differential work, is equal to the force dotted with the distance. Okay. And then if you want not the differential work, but the actual work, you just do an integral on both sides. Here, actually, why don't I box this, since this is kind of important. So if you want the actual work, you just integrate the force over the distance. Well, here, force is not the best quantity to work with since we're dealing with a gas. It's better to work with pressure, which is the force per unit area. So now pressure is the force per unit area. And if I look at my gas container, well, my piston has some area to it. Right? If I look at the bottom of my piston, say it's a circular piston, it's got some area to it. And I am sliding my piston down by some amount. I'll call that amount dx. Okay. It's a bit too big. The way I've drawn it, it's a bit too big to be a dx because dx's are supposed to be small. Well, let's just assume that's a small distance, very tiny piston. But that would mean that my force, which can be written this way, my force is pressure times area, which would mean that my differential work is going to be the force times dx, which is the pressure times the area times dx. And if I look at what a dx is, it's the area, so that would be the area of my piston times dx. Again, that's your area, here's your dx. Well, that's just going to give you the volume inside this region. So this is how much your volume has changed by some differential amount. So we could write that the work done is the pressure times some differential volume. Now that is almost, it's almost what we want. However, I need to change one thing, because there's a question about what are we doing the work on. Am I doing the work on the piston? Am I doing the work on the gas? what are we doing the work on? Well, we're concerned with the work being done on the gas molecules. And we know that if I'm pushing my piston down, so if I'm decreasing my volume, if dV is less than 0, so I have a negative change in the volume, then what's going to happen is my internal energy has to go up. So I actually need a negative sign here. The work done on the gas, because I'm looking at the work done on the gas, if the volume goes down for the gas, so if dV is negative, I need positive energy added to the gas. So dV is negative, I have another negative sign. Negative times a negative gives me a positive. I get a positive energy out. So I want the work done is minus PdV if I want to compute the work done on the gas. You may have noticed I have a particular way of writing the D's on my differential internal energy. So I write dE, my internal energy, is equal to my work plus my heat. Notice that my D here is just a normal D, but the differential D here is a different D. It's got a line through it. Why do I write that line? Well, we have two different types of D here, and they do really mean different things. This is what we call an exact differential. These D's are what we call inexact differentials. Exact differentials apply to things that are state functions. So if I know, for example, the energy, that tells me about the state of the system. It's a state function. If I know the energy, I know what state the energy is in. However, work and heat are inexact differentials. They are not state functions. What that means is that it depends what path I take. So for example, let's just write out an example. Say I want to go, I want to take a gas and I want to compress it. So I want to move my piston down. Well, I can take different paths to get from this point to that point. But those different paths are not going to have the same work done. They must have the same energy, because the energy just tells me about the state of the system. So it doesn't matter how I get from here to here, I still have to have the same change in energy. That has to be exact. However, going from here to here, the amount of work that I do will depend on the path. Just to show that that's the case, let's consider two different paths. Let's say, actually, I'm going to put one more constraint in here. Let's say this is a hot temperature of a gas, and in here my gas is pretty cold. Well, I can go many different ways, but I'm going to consider two here. The first thing I'm going to do in this path is I'm going to compress my hot gas. I'm going to compress here, so that my piston is now moved down in the container. But when I do that, it takes a lot of energy to compress a hot gas, right? The gas molecules are banging up against the top of that piston, so it's going to be hard to push that down. I am doing a lot of work. So we could say that delta W, the work, is big. Then what I can do, let's say once I get to here, I clamp the piston down. The piston's where I want it to be, so I clamp it down. And then I cool it down to get to this temperature. Now I'm not doing any work here, because we have said that the work that we do depends on the volume change, and there is no volume change here. So there's no work done in the cooling stage. Now, here is a path where I do a lot of work. Let's consider a path where I don't do a lot of work. All right, well, if you're smart and kind of lazy, and you don't want to do a lot of work, you maybe you know that compressing a hot gas is not what you want to do. It's going to take a lot of energy to compress the hot air or whatever gas it happens to be. So maybe you said, all right, well, first thing I'm going to do is I'm going to clamp this down and then I'm going to cool it. So say I did this path in a different order. Say you cooled the gas first. We have room here. Cool the gas first, okay, with this piston clamped on. Okay, so I haven't done any work, much like I didn't do any work on this cooling stage. But now we have a cool gas. It's not going to take as much work to compress that gas because the molecules aren't moving very much. They're not going to be slamming into the top of the piston trying to prevent me from compressing it. So now we can do our compression again. And the work that I've done to compress this time is very small. Or at the very least, small compared to trying to compress the gas when it's hot. So if I were to try to take this path, I do a lot of work. If I were to try to take this path, I do a small amount of work. I still get the same change in energy. I've still gone from state A to state B. The only difference is the amount of work I've done. So that's what it means to be an inexact differential. An exact differential, we still get the same change in energy. Inexact, it depends on what path I take. Now, to be sure, I still have to have the same amount of energy going in and out. So if my change in energy is 10 joules, and along the top path I do 9 joules of work and get 1 joule of heat, I still have to have dW and dQ add up to the same thing. So maybe on the top path I do 10 joules of work and get 1 joule of heat transferred. And in the bottom path maybe I do 1 joule of work and get 10 joules of heat transferred. They still have to add up to give me 10 joules of energy change because energy is an exact differential. So let's recap what we've done so far. We said that energy is conserved and the only way to change the energy is to do some amount of work or some amount of heat. For a gas, any type of gas, we know that the work done on the gas is minus P dV. So what does that mean for us? Work done on the gas is minus P dV. How do we actually compute that? Well, if I want to get not just the differential work, but the total amount of work done, that is going to be, I can obtain that by doing an integral. So this is just going to be the integral minus P dV from V initial to V final. So it depends on my initial and final velocity. Now, the important thing to remember here is that my pressure can change. My pressure can be a function of volume. So we know that pressure can change on volume because of the ideal gas law. Or just thinking about it conceptually, if I push down on a container of gas, if I squeeze a balloon, the pressure inside is going to increase as I try to decrease the volume. So I know that pressure typically depends on the volume, though there are some circumstances where the pressure will be constant. Ultimately, the only way to really determine how to do this integral is to see what thermodynamic path we take. So if I were to plot the pressure versus the volume, let's say I wanted to go from this point, this volume and this pressure. So I'm at some V initial and some P initial. Say I wanted to go to this point. So I'm at some final volume and some final pressure. I'm going to end up at the same volume and same pressure. But the amount of work I do is going to depend on how I get there. So let's say the first thing I do is I stay at a constant pressure. And I go to this point. So I keep pressure constant, but I expand the gas to a higher volume. Then I decrease the pressure while staying at the same volume. So I go keep constant pressure, then I go down to a constant volume. I could compute the work done for that. The work done is just the integral of PdV, so the work done would just be the area under the curve. It would be just that area. So it would be this pressure times this volume. That's easy to do. However, there are other paths I could take that would give me a different work done. So for example, say instead of going straight across and then straight down, what I decided to do was take a different path. Say I took a curved path. So it turns out, if you maintain the constant temperature, you'll get a path that's a little bit curved that looks like this. Now this path is not going to have as much work done as my original path. Why doesn't it have as much work done? Well, I can see that in two ways. Mathematically, I can see that if I just look, if I try to compute the area under the curve, I can do that with my little box method, or I could just integrate. You can see I quite simply just don't have as much area. Right? This path has this much area under the curve. The original path had this much more area. Right? My original path going straight and across. Okay. Well, why do I have less work done now? Well, you can see my pressure is decreasing as I'm increasing the volume. So that means I am not pushing as hard to get my gas to be compressed. I don't have to push as hard if the pressure is constantly decreasing, as I do if the pressure stays at its initial large value of pressure. Okay, so these are two examples of thermodynamic paths I can take. In truth, I can take any number of paths to get from that starting point to that ending point. If I wanted to, if there were a good reason for it, I could come up over here, do some loop-de-loop, go all over pressure and volume space in a very complicated path. But still, at the end of the day, all I have to do is compute the area under that very, very complicated curve, and I'll still get the work done. So, all we have to do to compute the work is do an integral of minus PdV, keeping in mind that pressure could depend on the volume. There are many types of work that there are many systems that you can do work on. It's not just gases. For example, we could consider stretching a solid wire. So say I have some wire, and I apply some stress to that wire, so I pull on it. Say I fix this end, and I pull this way, and by pulling, make a small change in the length. We'll call that dl. Well, I'm doing some work on the wire. I'm giving it potential energy by stretching the wire out some distance. If I'm applying some force F, the work is pretty simple. It's just going to be F dot dl. So very similar to the original definition of work we saw before, F dot dx. Here, it's just going to be the force you apply to stress to the amount of strain you get in the material, which is equivalent to how far it's going to stretch. Bubbles! Bubbles! Bubbles, lots of bubbles. Yeah. Bubbles. Crappy bubbles. There we go. So bubbles. You make a bubble because you have some surface that you are stretching. And when you stretch that surface, you are inherently doing work on it. So that's another type of work. Let's consider a simple geometry for that. Let's say I take a coat hanger and I bend it into the shape of a U. And on that U, I put another wire that can slide back and forth. So if I were to dip these wires into a solution, a sub-solution that could make bubbles, what you would find is that if it's strong enough, the solution, the slip solution, would form a thin film along the edges of the wires. And that thin film has some surface tension to it. So surface tension does not like surfaces to stretch out. It wants to pull them back and contract them. So that means that if I want to stretch this bubble, I need to apply some force on it. And the force needs to counteract the surface tension. I'm going to call the surface tension, let's call that gamma. If I want to compute the work done by surface tension, I am applying a, so this is our surface tension. Now, so that you know what surface tension is, this is the amount of force you have per unit area. It's the amount of force you have to apply to get the surface to stretch by a given area. Therefore, the differential amount of work, dW, is just going to equal gamma times the change in the surface area. Okay. So I look at my bubble, I stretch the bubble by some change in area. Here we go, I pull it forward a little bit. Get some change in the surface area. The work I do is just equal, the differential work I do is just equal to the surface tension times the change in the area. Batteries. Batteries also have some work that you can do with them. In this case, it's electrochemical work. We have two chemicals. In this case, for the example I'm using, copper and zinc. They have different oxidation reduction potentials, which means there's a chemical potential difference between the two. What this means, let's just draw our potential difference here. In physics, we would say there's an electromotive force that will push charges between these two. So that, were I to connect a light bulb between these two spots, why don't I just draw a light bulb between those two? Light bulb. Since there's a potential difference, a chemical potential difference between those two, electrochemical potential difference between these two, that means charge is going to want to flow from one end to the other. So we're going to have charges that are going to be moving down, passing through our light bulb. Let's say we have the total amount of charge dz that passes through. Well, that means I can compute the amount of work done because the charges are going to feel an electromotive force. The amount of charge that I push is going to determine how much work I do. So the amount of differential work that I do is going to be just whatever the electromotive force is. It's how much or how strongly those chemicals are going to be pushing the charge times the amount of charge that you are going to be passing through. So work does not necessarily have to be mechanical. It could be electrical. Still the same thing, you're using energy to push charges around. And when you do that, you change the amount of energy that is stored in the battery. Batteries, much like anything else, are just another example of thermodynamic systems. Okay, say you have, we can also do work by changing other properties of a material. So say I've got some material, and I take that material and I connect it to some capacitor plates that are connected to a battery. So here's my battery. Well, we know that the battery is going to create an electric field because it's going to charge up those capacitor plates. So now, electric field points from positive to negative. There's an electric field through my material. Now, if that material is a conductor, charge is just going to flow through it and the electric field will go away. But most materials, not most, maybe most, many materials are not perfect conductors. They're going to polarize a certain amount. We call these either insulators or dielectrics. So what that means is if I look, let's say I look at my little atom right there, well, his electrons are going to move closer to those positive charges and move away from those negative charges. They're just going to move in response to the electric field. And what that's going to do is it's going to polarize that atom or molecule so that we have a positively charged end and a negatively charged end. Same thing for this atom over here. Same thing for these atoms. Plus, 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 minus, 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 minus. Right. It's just stretching the molecules out by moving the negative charges towards the positively charged plate and move the positive end of the molecules to the negatively charged plate. Right. Well, when you stretch those molecules, that takes some effort. That effort is just going to be in the form of energy. It's just going to be some work that you're doing. And you're creating electrical potential energy when you do that. So what's that going to be equal to? Well, it's going to be related to a few things, one of which is the thing that's doing the work is this electric field that you have created. And it is stretching the molecules by a small amount. It's stretching them by an amount which I will call dP. This is our polarization. So it tells me how polarized my molecules in my material, how polarized they're going to be, how much they're going to get stretched. So if I want to know the work done, all I'm going to do is I'm going to take how big of an electric field I have applied times how far the molecules are stretched, or how polarized the molecules are becoming. And then this will just give me my work. Just like any other system, I'm taking energy from, in this case, energy from my battery, and I am doing work on my material by stretching those charges out, giving them electrical potential energy. Okay, we've talked about polarization, which is how do I get the charges in a molecule to stretch when I apply an electric field. A very similar instance is magnetization, which is how do I get the magnetic spins in a particle to, or magnetic spins in a material to start to align when I apply a magnetic field. So let's say I have some material, maybe it's a piece of iron, maybe a piece of cobalt, some sort of magnetic material, and each atom has a certain spin to it. Now, if the temperature is pretty high, those spins are going to be randomly arranged. They've got enough thermal energy to just bounce around randomly. There's not going to be any magnetization. If we cool it down for certain materials like iron, cobalt, what we call ferromagnetic materials, we'll have a net amount of these spins aligning. But even if it's not a magnetic material, even if it's not a ferromagnetic material, we could still get those spins to align somewhat by applying an external magnetic field. So what I can do, let's say, not sure if that's going to show up good on camera, I'll use a green instead. Let's say I apply some magnetic field. We'll call that magnetic field H. This is the magnetic field. You may be used to seeing the magnetic field written as B. We're going to use H here. B reserved for magnetic induction. Worry about that when you get to electricity and magnetism, the 300 level class. We're going to call our magnetic field H. And we're going to look at how that changes the magnetization. So in principle, what could happen is we are going to get more magnetic spins aligned in the material. So we could, let's just flip a couple of these up. Okay, so now I start to get some net magnetization where these spins start to point in the direction of the magnetic field. We can talk about we can use a parameter to describe the fraction of these spins that are pointed up, and that's just called the magnetization. So as soon as I start to get a significant fraction of these pointing up, so that it's not 50% up, 50% down, this will start to actually act like its own magnet. So you could imagine that once I polarize this, we get a north pole and a south pole, just like you do on a refrigerator magnet. And just like when we applied an electric field, we got polarization of the molecules. Here we apply a magnetic field, we get magnetization of the part the molecules or atoms inside the material. So when we do this, obviously that's going to take some amount of energy to do. Energy is coming from the magnetic field that I'm applying. So we want to compute the work that we've done on the material. And as always, the differential work is just going to be written by the product of two things. We've got some magnetic field that we've applied. We've got some magnetization. So if I change my magnetization ever so slightly, I'll call it dm. We will get that the work that we're doing when we do this is just H dotted with dm. So my magnetic field dotted with my change in the magnetization. Okay. So we can compute our work done on a piece of magnetic material. So I mentioned iron being a piece of magnetic material. We refer to that as ferromagnetic. The model I'm working with here is actually called a paramagnet. So it's a paramagnetic material. So ferromagnetic materials, things like your refrigerator magnets, are materials that I don't even need to apply an external magnetic field to get them to magnetize. They're already magnetized without any help. Really what we're looking at here is a paramagnetic material. And a helpful way to remember that this is a paramagnetic material is because the spins, the directions that the individual magnetic spins are pointing, they pair up with the magnetic field. They pair up, so they're a paramagnetic material. There is a third type of magnetism called the diamagnetism. A diamagnetic material is a material which, when I apply a magnetic field, the spins actually try to point in the opposite direction. So if my magnetic field is pointing up, the spins will actively try to go against that field and try to cancel it out. The way to remember that is that it's a diamagnetic material. So it wants to kill the magnetic field. So the magnetic field of the spins is pointing in the opposite direction. So we have three types of magnetic material. Ferromagnets, which you can think ferro is like iron, which is usually what you, which is oftentimes what your refrigerator magnets are made of. They have a permanent magnetic moment. Paramagnetic field has the magnetic moments try to match up with any external magnetic field. Diamagnetic materials want to kill that magnetic field, so they point in the opposite direction to try to cancel it out. The model we're working with here, that is for paramagnetic material. So we're working with materials that want to pair up with the magnetic field. So we've talked about many different types of work. We've talked about work on a gas, work on a stretched wire. We've talked about stretching a surface. We've talked about polarizing a material. We've talked about magnetizing a material. We talked about, didn't have room for this one on here, but electrochemical work. There's many more examples. My list is by far not exhaustive. There's many different types of work. But we want to be able to generalize what we mean by work. And to do that, it helps to write our work equation in this form so that we know that there's many different types of work that could go on. So I'm not restricted to just having a gas that does nothing else other than be a gas. I could have a gas that has magnetic particles in it, or polarizable particles. I could have a solid that has some stretchiness to it, or some polarizability. A lot of different things we could do that would be considered work. But there's an interesting trend that builds up if I look at some of these different terms and see how they work. So for a moment, let's just look at the differentials. So I have a differential volume, a differential length, a differential area, differential polarization, differential magnetization. All of those quantities, length, volume, area, polarization, magnetization, they are what we would call extensive variables. So these are extensive variables. What I mean by extensive is that they extend with the system. So for example, if I were to double the size of my system, I would get twice as much volume. If I were to double the length of my wire, double the size, I would get twice as much length. Similar for these things. They change with the size of the system. Now, let's contrast that with the non-differential variables, these guys. So our pressure, force, surface tension, electric field, the magnetic field, all of these are the same throughout the system. So we have pressure, force, surface tension, electric field. The electric field is going to be the same everywhere throughout the system, as is the pressure. These, since they're the same everywhere inside the system, they don't extend with the system. These are called intensive variables. So we have extensive variables and intensive variables. And in general, whenever I write the thermodynamic work done, we can write that as, I'm going to do this generally now. I could write it as some intensive variable times some differential extensive variable. So we'd have some extensive variable times some differential intensive variable. To get the work, you want to integrate over these. Now, The x could be pressure, could be force, could be any extensive variable, or intensive variable, excuse me. X can be any extensive variable. The differential, did I say that right? Say that one more time. The x can be any intensive variable. The dy can be any extensive variable, any variable that extends throughout the system. This is a generalized formula for work. It should work with any system that we're working with, whether it be the DNA dynamics or whether it be magnets, and superconductors. We should always be able to write our work in some form that looks like this.